Let's work through another macro example, this time about tracing the execution of a recursive function or procedure. We've been tracing recursive calls in this course before. In Python, we did it with a decorator. So here's a decorator called trace. It takes in another function to be traced, defines a version of that function that has the same return value, but before returning, prints the fact that this function is being called. Now this f string has one component before the parentheses, which gets the name of the function being called. And if you haven't seen this before, this is just how you take a function and look up its intrinsic name. Then it's got some parentheses and another expression, which is the argument value that the function's being called on. Here, I've defined factorial of n recursively. If n is 0, return 1. Otherwise, return n times n minus 1 factorial. By placing the trace decorator before the def, fact is not actually bound to the factorial function, but instead to the return value of calling trace. So fact is bound to this traced version of factorial, which, when called on some number like 5, will print out fact 5, and then call fact on 5. So now we're in here, and when it makes the recursive call to fact 4, it's in fact calling the traced version. So if I were to call fact 5 after tracing it, I would see that fact 5 calls fact 4, calls fact 3, 2, 1, 0. That all returns eventually, and you still get the same result, 120. So the lines that say fact are all printed, and this is the return value. Could we achieve something similar in Scheme? Well, there's no decorator syntax in Scheme, and it seems awfully hard. So what can we really do? Well, here's something we can do without using a macro. We could define factorial of n as a procedure that has the same logic as the Python version. We could then assign the symbol original to this fact procedure and redefine the fact procedure as a function that first prints and then calls the original. It prints a list that contains the symbol fact and the number n, and with this you'd get the following output. Pretty similar, right? The thing that's different is that there's a separation of concerns in Python, where writing fact doesn't mean I need to know anything about tracing. Writing trace means I don't need to know anything about factorials, and the only thing that connects them is this nice little decorator syntax. Whereas in Scheme, we wrote the same logic of a traced function, but we had to explicitly call it fact in order to make sure that when the original fact function makes its recursive call, it ends up back in the printing version so that you not only print fact 5, but fact 4, 3, 2, 1, and 0. So could we somehow generalize this in Scheme instead of having to re-implement this print logic for every function that we want to trace? Could we come up with something like the trace decorator where you write it once and use it over and over again? Well, let's explore that idea and write a macro. Here's the factorial procedure, and what happens when you call fact 5 is that you get 120, but you don't get any printed output. In general, the way you would get printed output would be to give some other symbol to the recursive procedure, then redefine fact as a procedure that first prints and then returns. And now when we call fact 5, we get the traced version. So originally, it gave 120 before we traced it, but then when we redefined it and called fact 5 again, we saw all the output. What we're going to try to achieve is a situation where sometimes when you call fact 5, you're tracing it, and sometimes you're not. In order to get back to the situation where we're not tracing it anymore, we would need to define fact as the original, at which point if we called fact 5 one last time, we'd see that before we trace it, it's 120. After we retrace it, it gives us the printing and 120, but then when we go back to the original, it just shows us 120 without the tracing. In order to build this logic into a generic macro, we're going to have to turn it into one expression instead of 4. So that means writing a begin. And this begin is going to first define the original, then define the new version, then call it. Now, if we want to make sure that this begin expression has a value, we need to capture the result of calling it. Then we switch fact back to its original form, and we return the result as the value of the begin. So running this will give us the same output, where this is now one big expression, which shows us the traced version of calling fact5. And now the trick is to write this down generically. But since it has a bunch of defines in it that are changing the way fact works, I don't think we can write this as a standard procedure. We need it to be a macro, which traces some call expression to a recursive function. We'll call that expr. And this is going to be something like trace fact5 to give us the traced version. So if you're tracing fact5, you're going to have to print out fact. That's the operator symbol. Let's give that a name. Operator is the car of the expression. So that's something like just fact. And then we have to build this begin expression. So that means quasi-quotation. When we define original, we don't want it always to be fact. We want it to be whatever the operator is. And so we use unquote in order to make sure that the operator gets evaluated. Then we redefine whatever the operator is, such as fact, to be a new lambda that prints out list. Instead of always printing fact, we want to print out the operator, and then the argument n. Now we still need to call the original on n. That's part of the code that we generate. When we define the result, instead of calling fact5 every time, we want to call whatever the expression is. That's, for example, fact5. And finally, we set the operator back to whatever it originally was, so that if somebody calls it again, we don't see some different result. And then we return the result, we close the begin, we close the define macro, and now we can trace fact5, and we should see a traced version. Now there is one problem with this version. Let's take a look at what it is. We define fact, call it 120. We build our macro, which is a trace macro. When we apply our trace macro to fact5, we are printing a bunch of stuff before computing 120, which looks good, but we're not printing fact5. Instead, we're printing out the fact procedure, which looks like that. But we really just want to print out the fact symbol. We would achieve that by quoting that symbol, which generically is called operator. So if we run this again, now we see what we were looking for. Calling fact5 gives me 120. Tracing fact5 shows me what happened and gives me 120. But if I call fact5 after that, everything is back to normal because I went back and defined fact as original again. And the nice thing is that this trace macro doesn't refer to the fact procedure at all. It just assumes that expr is a call expression of any procedure that's potentially recursive that takes one argument. The reason it has to take one argument is that we defined this lambda as one argument. But you could try to write a more general version as well. And now we've achieved the same separation of concerns that we saw in Python, but this version's even better than Python's, because in Python you had to decide whether fact was always traced or not, depending on whether it was decorated, whereas in the scheme version, we can call fact5 untraced sometimes and traced other times and even switch back. So it's really whether we trace an expression, a call, rather than whether we trace the whole procedure permanently, and that gives additional flexibility. Cool.